Hi everyone, in this video walkthrough we'll be going over problem 4b on CS61BL Summer 2021, the final. So this problem I think is kind of clever and it's kind of fun to go over, so yeah, let's kind of see what's happening here. So for the following two parts, we'll be calling LSD sort with conventional LSD sort as the subroutine, and conventional LSD sort uses counting sort as the subroutine. So in this instance, we're kind of doing like recursive LSD sort, where we're running LSD sort, and then on each digit, we're calling LSD sort again. So I think it's kind of cool, kind of a weird idea, but let's see how it plays out. So since conventional LSD sort requires that the object it's comparing are comprised of digits of a fixed radix or base, we will decompose each character from the alien alphabet into a number of a certain radix. Okay, so I think this might be a bit confusing. So looking at this image below, if we have the blue, green, red, and yellow strings, what we're going to do is we're going to translate each of these characters to base 10. Okay, and I just kind of chose this base arbitrarily. It happens to be like the first part of the problem. So we have these in base 10, right? Notice that they just happen to be these numbers. I just chose them randomly. Now what I'm going to do is run conventional LSD radix sort on these numbers. Because now that each character is represented in base 10, notice that if I run conventional LSD radix sort, it works pretty well because I'd look at all of these digits here, right? Okay, so I run conventional LSD radix sort. Now these are sorted, and then I complete the pass and sort all of these strings, right, based on the result of running conventional LSD sort on that digit. Okay, so yeah, I think that hopefully makes sense of what's happening there. Let's actually look at one more example just so we really fully understand it. If I'm looking at the help Anna meet with rats example, what's happening here is that it's kind of mirroring this process. I think that might be helpful. When I look at help Anna meet with rats, let's look at the first pass when we're at these digits. Okay, so the first thing we're going to do is translate them to base 10. So moving to the world of base 10, I know A is 1. I actually don't know what S is in the alphabet. What did I say last time? I feel like S is 19 or T is, so let's just say it's 19. This is 20. I think H is 8. And let's say P is like P, Q, P is 16 then maybe. Sure. Okay, so we move in the world of base 10. That's like the first step here. And the next step here is that we're going to run LSD radix sort on these digits, right? So when we run LSD radix sort, notice that we'll compare the first digits in all of these, and then I will run counting sort on these digits here. So once these numbers are finally sorted using LSD radix sort with counting sort as a subroutine, they'll be in this order. It'll be like 1, then 8, 16, 19, 20. Right? So these are sorted. And then what I'm going to do is, now that we've sorted all of these digits, let me just kind of write the digits back. We know that P is going to track where they all went. So what we can see here is that we're looking at the final answer, or not the final answer, the final result of the first pass. We have help, came down here. We have Anna, went up here. We have meat here. We have width here. And then we have rats. Okay, so after doing the first pass, we'll see that this is our result. And then we're going to repeat this process, right? This is going to be pass 1, where we're looking at this digit. And then if we look at pass 2, it's going to be the same process. So now we're going to be looking at this digit here, right? And then we're going to repeat this behavior. So it's a bit more complicated than before, but hopefully this example kind of illuminated what's happening here. So the problem continues to say, for each part below, find only the worst case runtime of calling LSD sort with LSD sort as the subroutine. Okay, if we decompose each character into a number of the given radix. So in this example, we just converted all of these numbers into base 10 because that's really easy for us to understand as humans, right? But it's possible we can use another base. So some other bases that exist is that I can decompose any number into base 2, right? If I take 16 and I make it into base 2, it's going to look like a bunch of ones and zeros, right? It may look like 1, 0, 0, 0, 0. Sure. Okay. I might have done one too many zeros. 1, 2, 4, 8. Okay, no, I think it looks good. So that's like if I decompose 16 into base 2. You don't really need to understand it, just the idea that there are more bases that exist, right? So with this in mind, let's look at the problem. So the problem starts off with the radix 10 or base 10. Okay, so that's basically this example that we have right here. And how I kind of want to approach this is that we know that the runtime of LSD sort, and this is like the highest level LSD sort, right? This high level one, and then this one we call in each digit, is going to be W times the runtime of our subroutine. Okay, well now, the runtime of our subroutine is going to be LSD radix sort with counting sort as the subroutine. So this is going to be W prime times of counting sort. Right? And the reason I use W prime here is because we don't really know the width of these numbers, right? So that's what W prime is referring to. It's referring to the width of the numbers that are passed in to LSD radix sort, right? We know the width here, that's the W that's given. This W prime is some width that we need to figure out, right? Well, we know that the runtime of counting sort is n plus r. So we have kind of this right here. We need to figure out, when I'm looking at the subroutine, we know its runtime is W prime times n prime plus r prime, where W prime is the width, n prime is the number of elements, and r prime is size of radix, right? So all we really need to do to solve this problem is just kind of figure out what these are, right, for these numbers here, okay? So the easiest one is that n prime is just n, right? Because the total number of elements to our subroutine, right, when I'm running LSD radix sort here, is still n. We still have n elements, okay? So we know n prime is n. And then r prime is also easy. It's the size of our radix. So in this case, the problem states that our radix is 10. So let's just put 10 here. So all we really need to figure out is the width of each one of these numbers, right? Well, all that we're doing here is that we're decomposing, right? When we think about this width, we're decomposing a number of size n squared into a number of base or radix 10, okay? So, and we're trying to figure out how many digits are in this number, right? And so kind of looking at the hint states that if we decompose a character of size m into a number of radix b, the number of digits in the resulting number is log a base b of m, okay? So let's kind of use our hint to help us a bit, right? So with this hint in mind, notice that we are decomposing a number of size n squared into a number of radix 10. Actually, use a different color. And the number of digits in the resulting number is going to be log base b, well, b is 10, of m, well, m is n squared, right? Okay, so we have log base 10 of n squared, and what we know here is that log base 10 of n squared can be simplified, right, to 2 log base 10 of n. Okay, so what we'll see here, and the reason this simplification can occur is because of this hint that log okay, that's why we can do the simplification. So then if I'm looking at the width, we know it's log base n. Okay, so the width here is going to be log base 10 of n. And notice that like the 10 doesn't matter because it's a constant, so just log n. Okay, so when we're looking at the final runtime, we can plug in this piece here. I can plug in this piece here, and then I can plug in this piece here, right? And what I get for the runtime of the subroutine is going to be log n times n plus 10, which is equal to n log n, right? So now I can plug in n log n as the runtime of the subroutine, and then I get wn log n, right? So that's going to be the answer to the first part. It's just wn log n. Cool. Yeah, definitely a very tricky problem. So moving on to the next part, now my radix is going to be n. And not too much is different. We can kind of really mirror the same exact thing we did here. We can just change some of the logic. Okay. So I'm just going to duplicate this, move this down here. So we're still doing the same exact thing. We just need to figure out what's changing now. Now what's changing, let's use like a color to highlight this change. Let's do black, sure. So notice that R prime changes into n now, and then W prime is going to change too, because W prime depends on R prime, right? So if now that I'm decomposing a number of size n squared into a number of base or radix n, the number of digits in this number are going to be, right, by the same logic here, it's going to be just highlight it again. It's going to be log base n of n squared. Okay, so now we can use the same step again. Okay, so now what we can do is we can say, I can use this property to move the 2 to the front. So now it's going to be 2 times log base n of n. And then finally, we can use the third hint. So cool, using all these hints. I feel like a beast. Right, the third hint here is that notice that when the base and the exponent are the same, or the base and the number, this simplifies to 1, so this is the same as 2. So basically what we've shown here is that our width is going to be 2, okay? So kind of going back up from here, now that w prime is 2, we can plug that in here, okay? And now what we'll notice, which is really cool, is that when I'm looking at this runtime, right, notice that it's this orange times this green times this yellow, or this kind of plugged in, okay? Notice that we get 2 times n plus n, right, which is just equal to n asymptotically. So now that we know the runtime of the subroutine is n, plugging it in, we get w of n as our answer. And I think the coolest part of this problem is that it seems like we're kind of doing random stuff, but what we'll realize is the runtime of this modified LSD sort of wn is the best runtime we've achieved so far out of every single sorting algorithm up to this point in the problem. So although in an exam it's kind of hard to appreciate it, I think it's pretty cool that if we use LSD radix sort recursively, it might work in some situations. So we can see here that the runtime is wn. Okay, so that is all for this video walkthrough. I hope you all enjoyed it, and yeah, well, I'm guessing you're probably going to be watching this in a later summer. Maybe you'll be watching it now. But anyways, hope you have a happy studying for your exam.